Okay, Chem 11, 10 students, we are down to the last part of Chapter 5. And this is an extremely important part because we're going to be talking about the molecular mass of compounds and then how we can use an empirical formula and the molecular mass to determine the formula for something that was previously unknown. So, important part. So we're going to talk about molecular and formula mass. The molecular mass is the mass in atomic units of an individual molecule of some particular kind. So to calculate this, you multiply the atomic mass that you would find on the periodic table for each element by the number of the atoms of that element that are in the compound, and then you would add them all up. So for water, you would take 2 times the atomic mass of hydrogen plus the atomic mass of oxygen. So it's 2 times 1.008 AMU plus 16 AMU is 18.02 AMU, and that's correct significant figures. Because we were adding, we can only have 2 decimal places. The atomic masses are on the periodic table are the average atomic masses, so therefore what you are going to get is the average molecular mass, and sometimes that's called the molecular weight. All right, so sometimes an ionic compound does not truly have a molecular mass. We can use its empirical formula, or that formula for a unit, that NaCl or LiCl, to determine its formula mass, or the mass of a unit, sometimes called the formula weight. Process is the same, so you multiply the atomic mass off the periodic table by the number of atoms that are present. So we've got some examples here. We have propane, which is an organic compound, lithium hydroxide, which is inorganic, and in fact it's an ionic compound, or barium acetate, which is also an ionic compound. And so if you remember, we're going to determine that molecular mass, or the formula mass for the ionic compound, by summing up the atomic masses. And so when we look at these, propane, we have 3 carbons, 3 times 12.01 plus 8 times the atomic mass of hydrogen, which is 1.008. Lithium hydroxide is LiOH, and so lithium is a 6.941 AMU, 16.00 AMU is for the oxygen, and 1.008 is for the hydrogen, and so on. In barium acetate, if you look back at the formula, the C2H3O2 is in parentheses with a 2. Subscript. So you have to multiply that through. So you actually have 4 carbons. So you're measuring 4 or multiplying 4 times 12.01. 6 hydrogens, so it's 6 times 1.008, and 4 oxygens, 4 times 16.00. Now remember, I told you, depending on what periodic table you use as to what the average atomic mass is going to be, the one in this text, Burge and Overby, uses 16.00, so only 4 significant figures for oxygen, whereas the periodic table we prefer to use has 15.999, which would round to 16.00. Okay, another important way that we talk about compounds is by percent composition, and that's by mass. And so you would use N times the atomic mass of the element divided by the molecular or formula mass for the compound. And because you want it to be a percentage, you multiply by 100. So N is, the number of atoms of a particular element. And so I have an example here. If you're looking at hydrogen peroxide and you want to know the percent of hydrogen in it, there are 2 hydrogens, so it's 2 times 1.008, and the entire formula mass for hydrogen peroxide is 34.02 multiplied by 100, so the hydrogen is just under 6% in terms of mass. And the oxygen is the rest of it. And just a note, if you are doing percent composition by mass, your percents should add up to 100%. All right. The other thing that we are going to look at are empirical formulas. Remember, we talked about those previously. It's the simplest formula. So hydrogen peroxide, which is H2O2, the empirical formula is just HO. And you can do that same calculation using the empirical formula mass to do the same calculation, and so you get the same numbers. So that empirical formula represents the molecule extremely well. All right, so here's another example of percent composition. And this is for lithium carbonate, which was one of the first drugs that was approved by the FDA for manic depressive illness. And so here we're asking you to calculate the percent composition by mass for that compound, lithium carbonate. And so you go through and you do the lithium, the carbon, and the oxygen. And once again, these need to add up to 100%. All right, so now we're going to talk about molar mass. We have been talking about the mass of a molecule in terms of AMU, whereas a molar mass is the mass in grams of 1 mole of a substance. Well, it turns out that the way the AMU is defined, the average mass of a carbon atom is 12.01 AMU, whereas 1 mole of carbon is 12.01 grams. And so that equivalency makes it very nice for our calculations. And so to get the molar mass of the compound, you just sum the molar masses of the elements it contains. And so for water, it would be 2 times 1.008 grams. This is grams per mole. For the hydrogen, the oxygen is 16.00. So you get the same number, but instead of 18.02 AMU, you get 18.02 grams for 1 mole of water. And sodium chloride comes out to 58.44 grams in a mole. All right, so we have to be very careful when we're talking about the molar mass of elements such as oxygen or hydrogen, naturally occurring elements, to specify the form of the element that we need. Because oxygen in our world predominantly exists as O2, but you might be talking about atomic oxygen. You also could be talking about ozone, which is an allotrope, and so you have to know which form you are talking about, and you can see how the masses would vary based on what you're talking about. Here's a little diagram very similar to what we had done before in going from the mass of an atom to moles, and in this case we're talking about atoms, molecules, or formula units, and we do all the conversions the same way. If you're going from grams to moles, use molar mass. If you're going from moles to particles, then use Avogadro's number. All right, so I have a couple of examples. Determine the number of moles of carbon dioxide in 10 grams of carbon dioxide, and then another example for sodium chloride. So once again, you're going to use that molar mass for the conversion. So carbon dioxide is 44.01 grams per mole. Sodium chloride is at 58.44 grams per mole that we discussed earlier. So for 10 grams of carbon dioxide, you could draw this out as a dimensional analysis. That's what this really is. It's just not in the railroad track form. But grams of carbon dioxide cancel and you're left with moles. Same thing for the sodium chloride. Here's another one. Determine the number of water molecules and the number of hydrogen and oxygen atoms in 3.26 grams of water. And a similar one, determine the mass of that many molecules of carbon dioxide. And so you need Avogadro's number in this case, and you're going to use some molar masses, as well as the molecular formula for water. And here is the solution. So for the 3.26 grams of water, you use that molar mass. And so your grams cancel and you have moles. And then we were asking for the number of hydrogen and oxygen atoms. So you're using Avogadro's number and you get the number of water molecules. Knowing there are 2 hydrogens in every molecule, you would double that number to get the number of hydrogen atoms. The number of oxygen atoms would be equivalent because there's only 1 oxygen in each molecule of water. And then here is the solution for the question about carbon dioxide. So you have the number of molecules, you divide by Avogadro's number, and that is going to give you moles of carbon dioxide, and then you multiply by the molar mass of carbon dioxide, which is 44.01 grams per mole, and you end up with the total mass of carbon dioxide in that, or the mass for that number of molecules. All right, so maybe we want to determine the empirical formula and the molecular formula from percent composition. And so what we're going to do is use that empirical formula, which gives us the ratio of the atoms in the molecule, and use that. We know the approximate molar mass, we can determine the molecular formula. So you divide the molar mass by the empirical formula mass and then multiply all the numbers obtained in order to get that molecular formula. So here's an example. You have the empirical formula, or you want to determine the empirical formula of a compound that is 30% nitrogen and about 70% oxygen by mass, and you know the molar mass is 92 grams per mole. So assume you have 100 grams. And if you do that, then 30.45% is going to be 30.45 grams. So you got moles of nitrogen and moles of oxygen, which would give you a really silly formula, but you can come up with a whole number ratio by dividing by the smaller number. So you're going to divide the subscript for nitrogen and oxygen by the smaller one, which is 2.73. And so 1 nitrogen, 2 oxygens gives you an empirical formula of NO2. With that, you know the approximate molar mass. You calculate the empirical molar mass. It only comes up to 46.01. You divide that into the 92 and you see that you need 2 of those empirical formulas to come up with a molecular formula, and so the formula is N2O4.